Hello and welcome. I'm Dr. Syed Mostafa Safavi, and you're listening to our podcast series on deep learning for intrusion detection. In this series, we explore how cutting-edge AI techniques are reshaping the way we detect and respond to cybersecurity threats. This podcast is produced with the valuable support of Alicia Tan, who has been instrumental in coordinating and preparing each episode. Now, let's get started and dive into today's topic. Welcome to the session, folks. Today we're diving into some pretty fundamental aspects of machine learning and deep learning, especially in the context of intrusion detection. We'll explore how sample data from a population is used to build models and how that ties into things like supervised learning.
Right, and when we talk about supervised learning, the key, as I understand it, is that the labels for our data come directly from human intelligence. Isn't that so? Exactly.
So, the training set is basically a sample from the entire population, and we're trying to fit a model that relates these input attributes, like characteristics or features, to a target response. It's like you have a huge ocean of potential inputs and outputs, but practically speaking, we only see a sample of that.
And that sample, once it's large enough, we assume it captures the essence of the whole population, right?
Right, exactly. It's like, if you taste a spoonful of soup, you hope it represents the whole pot. And speaking of representing data, the input also covers some fundamental statistical concepts, such as independent events, covariance, and correlation.
Yeah. Could you expand a bit on that correlation bit? How does it fit into this machine learning puzzle?
Sure. So correlation is essentially the normalized covariance that helps us understand the linear relationship between two variables, ranging between 1 and 1. Positive correlation means as one variable goes up, the other does too, while negative means one goes up as the other drops.
Got it. And then we move on to summarizing data. The basics like mean, median, and mode, which while they give a central tendency, don't quite capture variability, do they?
Exactly. The mean, median, and mode summarize data by a single number, but you really need to talk about variability. If two systems have the same mean, you typically prefer the one with less spread or variability. That's where concepts like variance, standard deviation, and the coefficient of variation come in. It's like when you're comparing two products. One might be consistent, and the other wildly unpredictable.
That makes sense. You want reliability. And about variability, I remember they mentioned something about summarizing it with confidence intervals as well, to give a probabilistic handle on the range of most systems.
Yes, absolutely. The input underscores how a single sample, or even a single number, isn't enough to fully describe a system. Instead, by employing statistics like confidence intervals and, statistical hypothesis testing, we can make probabilistic statements about whether any differences we see are truly significant or mere chance.
So, if I get this right, in hypothesis testing, we start with a null hypothesis saying there's no real difference and then perform tests to decide whether we reject that or not.
Exactly right. You compute statistical tests, and if evidence is insufficient, you retain the null hypothesis, meaning any observed differences could just be noise. But if the test shows sufficient evidence, then those differences are real, and that's a strong indicator about model performance variations.
Speaking of models, the input also takes us through building a model, starting from the crisp DM process, through feature selection, and ultimately to algorithm selection. How does that whole process connect?
Well, the crisp DM process is essentially a systematic approach to data mining that starts with understanding your business and data, moves through preparing and modeling the data, and finally evaluating the results. In our context, the features or predictors are selected carefully from the dataset, like the house features example provided, and then, based on those features, you choose the right algorithm, keeping an eye on the bias variance trade-off.
Here's where I want to throw a small challenge. Sometimes focusing too much on the bias variance trade-off might lead you to oversimplify the model. Don't you think complex systems like intrusion detection require a bit of nuance that simple statistical measures might gloss over?
That's a really good point. You could say that while simpler models might yield high bias and underestimate the system's intricacies, overly complex ones run the risk of high variance, meaning they might react too much to minor fluctuations. It's all about finding the sweet spot where the model is complex enough to capture essential patterns, but not so complex that it overfits the data.
Right on. And on the subject of overfitting and underfitting, the input makes it clear that you have to balance these carefully, ensuring that your training set is representative, but still keeping an unbiased test set to evaluate performance.
Yes, exactly. The practice of splitting data into training, test, and sometimes even a validation set is critical. It helps prevent data leakage, where information from the test set might inadvertently sneak into the training process, causing overly optimistic performance estimates.
Yeah, absolutely. I find the section on K-fold's cross-validation particularly interesting. It's like a safeguard against overfitting, right? You repeatedly test the model on different folds to ensure its generalizability.
Absolutely. K-fold's cross-validation, often with K set to 5, splits the data into folds, and then, for each iteration, treats one fold as the validation set while training on the others. It averages the errors across these folds to provide a more accurate picture of how the model will perform on unseen data.
It's like having multiple mini-tests rather than one big exam, a rigorous check on the model's resilience.
Exactly. And that's particularly essential when you're dealing with smaller data sets where every sample counts. Moreover, this method really highlights the importance of using all available data efficiently while maintaining fairness in model evaluation.
Right. Switching gears a bit, let's talk about the deep learning element for intrusion detection mentioned in the content. How does all this theory tie into actually detecting network intrusions?
Great question. Essentially, the same principles apply. You have labeled data, you extract relevant features, you build a model that understands the relationship between those features and a potential intrusion signature, and then you evaluate that model rigorously using methods like cross-validation. The twist, though, is that in the security realm, the cost of false positives and negatives can be huge, so the model must be finely tuned to balance sensitivity and specificity.
Exactly. And I suppose that's where unsupervised learning methods, hinted at in the further reading, come into play for detecting unknown or adversarial attacks. They can offer a complementary perspective to supervised methods by spotting anomalous patterns.
Totally. Unsupervised learning can be a powerful tool for identifying patterns in data that we might not even have prior labels for, which is crucial when you're dealing with evolving threats in intrusion detection. The content even points out some fascinating further reading on how these methods may help in detecting adversarial attacks and in understanding aspects of intelligence from AI-designed chips.
Yeah, it's impressive how everything from the basics of mean and standard deviation to complex topics like bias variance trade-offs all come together in such a practical, high-stakes application.
Absolutely. It's like, constructing a massive layered safeguard where every level, from basic statistical measures up to the sophisticated algorithm selection, plays a critical role in making sure the model works not just in theory, but in the real world.
And that's the beauty of it. You're essentially building a fortress against cyber threats using a blend of rigorous math, thoughtful data splitting, and smart algorithm design.
Exactly. And while there are challenges, like the risk of overfitting or data leakage, adhering to these robust methodologies ensures that the model remains reliable. It's a dynamic ecosystem where both data engineering and statistical finesse contribute to success.
So, I guess the takeaway is that a deep understanding of both the theory, the statistics, and fundamental ML concepts, and the practical nuances like model validation and intrusion detection specifics, is key to crafting effective models.
Absolutely. That's the core of it. Diving deep into these fundamentals provides the foundation upon which more advanced, application-specific ideas are built. And as our further reading suggests, this field is evolving continuously, with approaches like unsupervised learning pushing the boundaries even further.
It's a fascinating journey from understanding simple concepts, like central tendency, to tackling complex real-world problems like network security. I really appreciate how each step, from feature selection to cross-validation, is designed to ensure the model remains robust and reliable.
Well said. And it really highlights the interplay between theory and practice, something essential not just in intrusion detection, but in any domain where machine learning is applied. Balancing these elements is the key to innovation.
Absolutely. Thanks for this deep and engaging discussion. It's been great unpacking these comprehensive ideas and seeing how they integrate so smoothly across different layers of machine learning.
My pleasure. It's been an enlightening chat, and hopefully it sparks further exploration and discussion among everyone tuning in. Keep questioning and refining those models.
Until next time, let's keep pushing the boundaries of what these models can do.
Absolutely. Catch you all later.